the 16th of January. It's our second class meeting, and I think we've got some fun and exciting things that we're going to do today, including me getting to know you guys a little bit better. I meant to ask you this question with Blackboard or with Pull Everywhere, but for some reason I forgot it last time. So this is just to help me get to know you guys a little bit better. What's your favorite hobby? And I don't know if I mentioned it, but I have all sorts of different hobbies, including chainsaws. I think I talked about my chainsaws last time. No? I like chainsaws. I like cutting wood. I like skiing. I went skiing yesterday with my kids. Martin Luther King Day. I'm into kayaking. Kind of getting into kite surfing a little bit. Racquetball, basketball, frisbees, anything that's fun, basically. So, hockey, League of Legends. What's that? Is that a show or is that a video game? Video game? Is that like one of the ones on your phone that like little guys go around and fight each other? No. I'll have to look into that, I guess. All right, let's see what else we have here. Okay, art, baseball, basketball, board games, cooking, being outdoors, going broke. By that, do you mean going to college? Ever said that? Golf, guitar, hiking, photography, hockey, practicing the force. That's good. How's that go? Are you good at it? Whoever put that in? Getting there? Okay, good. Reading, self-improvement, shopping, sleep. We're good. It seems like we've got quite a array of different interests here. So I'm only going to show this because in my other class, someone brought up kayak, scuba diving. Someone said they like scuba diving, and that reminded me of a story that happened to me last summer that I thought was kind of fun and interesting. So I went kayaking on the Lehigh River with some people, and there was this cliff, and we saw some other guys jumping their kayaks off the cliff. So we said, well, let's do that. So I went up and jumped my kayak off, and one of my friends was standing on the top, and he said, "Here, let me take your phone, and I'll videotape you going off the cliff." And I said, "Okay." So I gave him my phone. It was in a dry bag, and I jump off the cliff, and I'll show you the video of that. It's kind of cool. And then he jumped in, and he said, "Hey, throw me that phone." And so someone dropped it to him, and thinking it would float if he didn't catch it. Of course, it didn't float, so it sank to the bottom. Anyway, I came back a couple days later with scuba gear, and I found not just my phone, but I found a $300 Invicta watch, $250 pair of sunglasses, a GoPro, 4 knives, another couple other pairs of glasses, and anyway, it was kind of fun. It doesn't have anything to do with statistics other than what is it we are trying to do with statistics? We're trying to find stuff, right? And you might think of that story as it's like a random sort of thing, but if you think about what goes on this river, this one particular cliff, lots of people jump off it, and so you might think of using that information. If I'm going to try and go scuba diving or treasure hunting or whatever, that's some information that I could use. And yeah, there's still some randomness. It took me quite a few trips up and down that little section to find all that stuff, but that's in some sense kind of what we're trying to do with statistics, and that is we're trying to find information or find the good stuff, the treasure that's out there, and we want to use whatever tools and and methods that we have available to us, but we also want to do that in kind of a, how would you put it, an intelligent fashion, right? We want to not just go out and randomly look for things. We want to use the information that we have already to help us improve on that. So I do have another question that I'm going to ask you guys, actually a couple more. This will help me gauge how much you guys watch the videos and that sort of thing. Okay, so what is a characteristic of a population called? It has a special name. And I'll hide this so you're not biased by what everybody else says. So far we have 10 results. There's 12. So keep sending these things in, and we'll just look at the response history, see if most people are saying here. Okay, so we have a parameter or sample, census, factor, parameter, sample, statistics, or a statistic. Turns out, are we getting any more? 21. Okay, so there's a bunch more that came in. Maybe we looked at that prematurely. Let's do it again. So the correct answer is a parameter. That's the characteristic of a sample. And just to help you understand, and there's a video that goes over this, and you probably saw this already, but I think it's important enough for us to get the big picture view of what we're doing in statistics. And when you get into your other courses and later in this class, when maybe you're bogged down by the details and you're saying, hold on, what's going on here? You can take a step back and say, okay, here's the big picture. This is what we're trying to do. This is how different things fit in. So what we're really interested in is not just the population that we're sampling from or the population that we're trying to sell stuff to, but we want to know the characteristics of the population, and those are called parameters. And these things are so important that we give them Greek letters for names, usually, not always, but usually. So things like mu, sigma, pi. This textbook uses pi for proportion, and that goes along with that convention. You might see p used as the proportion sometimes, and so forth. So we want to know about the population parameters, or the characteristics of the population. Why do we want to know about that? Because that's what we're going to base our decisions on. If we're manufacturing shoes, we want to know what the average size shoe is, or the average size foot is, and we also want to know how much variation there is in shoe size or foot size, and that comes from mu and sigma. And based on those things, we can now say how many of these different sizes should we make, and all that information comes from our estimates for the parameters or the characteristics of the population. So how do we know what the parameters are? Can we know for certainty what parameter values are for a say a large population? Small population, sure. But for a large population, typically we say that parameters are unknown, they're unknowable, and they're fixed. So why would we say that they're unknown? If we have a large population, why would we say they're unknown? Well, because we don't know what they are. Right? The only way to find out the characteristics of the population is to sample the entire population. So for interesting populations, why can't we do that? Let's say the population of the United States, for example. We wanted to know, pick some characteristic. Bank account content. How much do people have in the bank? I want to know that for the entire population of the United States. Why can't I figure that out?
It's too big of a sample.
Okay, the population's too big. Why is it too big? What do I need to do? Think about what I need to do in order to find out the content of everybody's bank account.
You need access to that raw data.
Okay, I need access to their banking information. Now, maybe the Federal Reserve, the government, has that information, but they're not releasing it to us.
You'd have to ask every single individual for their private information, but also, basically, you'd have to believe that they're actually telling the truth as well.
Okay, so there's two ways to do it. We could either look in the accounts ourselves, and we're not going to get access to that. So the other option is, let's just ask people. Okay, so who wants to tell me how much they have in their bank account? I'm not asking you to tell me, I'm just asking who wants to. Anybody? Nobody wants to do that. So, do I believe them if I can somehow get them to tell me that information? Is it accurate? Okay, well, but what other problems do we have? Situation like that.
Like room for margin of error as far as the accuracy of responses.
Okay, so there we could take into account, the accuracy back to this point. But what else? I want to know right now, this time, 10:15 in the morning on January 16th, what everybody's content of their bank account is. Is that even going to be that informative to me, even if I could somehow get all that information? No, why?
Well, you could argue that the sample's too small and it would be overgenerous.
No, we're not taking a sample. We haven't said anything about samples yet. We're looking for the entire population still. Well, let me ask you, has anybody taken anything out of their bank account this morning? I mean, maybe with a credit card or debit card or whatever. Yeah, so it's changing all the time too. So you can't get accurate information for the entire population because generally populations are too big in order to do a census. It takes too long, or the population is changing, and so that's one of the problems that we have there. So why, if we can't know what these parameters are and they're unknowable, what's the point in doing statistics? Or rather, how are we going to do this? Well, instead of looking at the entire population, we're going to settle for, it was mentioned a couple times here, for taking a sample. And the sample, of course, is going to come from the population. And as long as it's a representative sample from the population, and we do things like, say, this is for a fixed point in time, or if we're interested in time series data that we're not going to get into in this course, then we would have to say, well, here's our population, but we're looking at it sequentially through time. We can make statements about the sample, again, as long as we have a representative sample from the population. In order to be able to do that, there's a field of study that we need to use. Does anybody know what that's called? Okay, so if we know about probability, and assuming that we know what these parameter values are, or the characteristics of the population are, we can use probability to make statements about the sample. Okay, now you might be saying, hold on, that's counterintuitive too, because I just told you we don't know what these things are, right? But then I just said, if we know what they are, then we can use probability. So what do you think we're going to do? We're going to make assumptions. We're going to do, we're going to say, let's just assume that we know what the population mean is. If we know what that is, then we can use probability to make a statement about characteristics of the sample and how those let us make inference for the population. So another question then. And based on how well you guys did on the last question, I think you'll probably do well in this one. Okay, what's the characteristic of a sample called? So we have with characteristic of a population, it's called a parameter. What's the characteristic of a sample? And that's really, when I was drawing that picture, that's really what we're going to use to make statements about the parameters. So there we've got 13, 14, 15. I know we had a bunch more. So I guess there's a couple of ways we could score this. I could just look at these and say, of the 21 that got it right, that's not quite the full story. There's probably 60 people here today. So of the 22 that got it right, it's not out of 22, it's out of 60. So I guess we'll just go ahead and look at that then. All right, so statistic, data, demographic, population, stat. Okay, so statistic is the correct answer. And looks like of those that answered, most of you got that right, but most of you didn't answer. So let's come back over here and write this down. The sample characteristics are called statistics. And there's lots of different ways to use the word statistics. Here's one of them, characteristic of a sample. These are the things that we're going to denote with non-Greek letters. What are they? Is it Arabic letters? Whatever the, no, not Arabic. Whatever you call those things. English alphabet. So things like X bar, S, P, T, and so forth. So anytime you see one of these statistics, you should be thinking characteristic of a sample. Anytime you see a Greek letter, that says characteristic of a population. And that's really what we want to know. The test statistics, or the statistics, those are easy to calculate. Just have your computer or your calculator or your piece of paper and pencil. Calculate those. They're based on a formula usually, X bar. Just add up all the observations, divide by the sample size, and so forth. But we want to use these here to make statements about the parameters. And when we do that, going back this other direction, we have what's called statistics or inferential statistics. So there's again another use of the word statistics, and there are others as well. But this is the big picture. So when you get bogged down, and that probably will happen at some point, you'll be saying, you know, what's the parameter that we're interested in? Okay, mu, sigma, pi. Those are going to be the three that we really focus on in this course. Although we'll also look at for a linear model, beta 0, beta 1, and a few other things. To say, okay, what's the characteristic I'm interested in? Mu, let's say. If I know what mu is, then I can use probability to make statements about how likely the sample characteristic is that I see. Okay, and given that likeliness or likelihood, that allows me to come back and say, here is an estimate for mu. Now you might think that's actually a little bit backwards, isn't it? We're making an assumption about the value of the characteristic, and then we're going and collecting data and saying, does the data agree with that assumption? Has anybody ever heard of that process before? Yeah, it's called the scientific process, right? You have a hypothesis, and you go out and you collect data and say, does the data support the hypothesis? And if it does, then we go with that hypothesis, and we'll talk more later on about hypothesis testing in more detail as we get towards the end of the course. But that's kind of the big deal, the big takeaway from the course is this hypothesis testing or this inferential statistics. Now there are other ways of doing it. Instead of making an assumption about the parameters and then seeing if you can collect data to support that, you can just collect data and say, what does the data tell me? And that hopefully sounds like a better idea than saying, here's my hypothesis, let's go and collect data. Why is the hypothesis idea problematic sometimes? Can you think of why that might be? So somebody says, look, oh yeah, go ahead.
Sometimes you can't test the hypothesis.
Okay, sometimes the hypotheses are difficult to test. Okay, what else?
It's possible that it's already been answered.
Okay, possibly somebody's already answered it, maybe in a different discipline. Okay, those are those are problems that can show up. But what else?
You could have a bias towards proving the hypothesis true.
That's the real problem right there. Okay, did everybody hear what he said? If I think that what's a good example? If I think that the sun revolves around the earth like everybody else, and someone comes along and says, wait a second, no, I think it's backwards. I think the earth revolves around the sun. The earth's not the center of the universe. I'm now going to go collect data and try and prove that. Right? So everybody's thinking one way, and now someone comes along and says, well, everybody's wrong. Here's the right way to think about this, and now I've got to collect some data to prove that. So you come up with a theory, and then you go out and collect some data. Well, what if the data you collect doesn't prove your theory? Does that mean your theory's wrong? Or rather, the data you collect doesn't support your theory? Does that mean your theory's wrong? No, not necessarily. So in those situations, oftentimes researchers, scientists, general public, anybody that wants to prove their theory will go and collect more data. And they'll collect more data, and they'll just keep collecting data until what happens? They finally find some data that goes along with their theory. And because we said just because you find data or you don't find data, it doesn't mean your theory is true. Eventually you're going to find some data due to randomness or error that will support your claim. And that's problematic. So that's something that you have to be very careful about, and it actually causes a lot of problems. And there's all sorts of examples throughout history of that being the case. In fact, who's the guy who's considered the father of genetics, modern genetics as we know it? Is it Mendel? He did the experiments with the peas, and he had this great theory, right, about genes and whatnot. Well, it turns out that his data was fake. He proved his theory, but he fudged his data. He made up data to prove his point. And so, years and years later, I guess he was right, or actually he wasn't right, but every time you prove something, you find out life's more complicated, right? So he had some good things to say about genes, and that's kind of formed the model that that genetics is based on today, but it turns out he wasn't completely right about that, and that is partly due to the fact that he just made up his data. Okay, this is something that you did not see in the videos, because I did not mention it. But what is the characteristic of an individual called? And so think about this. We've got populations, that's everybody in the population. We've got a sample, that's a randomly selected subgroup of the population. And that's made up of what? Individuals. So what do we call the characteristics of the individuals? And this is, I don't know if it's intuitive or not, but let's see how you guys do with this. We got 20 observations, or 20 results. Let's just look at what you guys are saying here. Variables, trait, that is good. So we have characteristic, bias, data, observations, phenotype, traits, variables. Variable is the correct answer. Okay, so we have variables. Those are the things that change from individual to individual. So that's what we're going to use to describe the individual samples. Okay, so next question. So when I did my PhD at Duke University, which is in North Carolina, and I was married at the time, and I still am married to the same person, even though when you hear this story you might wonder why. My wife, we moved to North Carolina for me to do a PhD, and she worked like a year and then was bored and said, I want to go back to school. So she got a job, got into graduate school at the University of North Carolina. So we lived 3 miles from Duke, 5 miles from North Carolina, and I studied statistics and she studied city planning, and she had to take a statistics course. And so the first day in the statistics course, they said, look, you guys, city planning's interesting, and it's closely related to another field that you might want to consider switching your major to. And everyone said, what's that? And they said, geography. And I said, why would we want to switch to geography? And they said, well, that's because of the starting salary. So what do you guys think the starting salary is for UNC, University of North Carolina, geography majors? This would be very telling. So we're talking average starting salary for UNC geography majors. I mean, think about what geography is. It's like knowledge of lakes and streams and capitals and boundaries and mountain ranges, right? That's geography. And this was before the days of Google Earth and all the mapping stuff and all that. So we got 33. So here's what we have: 20,000, 40,000, 65, 40, 600,000. I don't know if that's a typo or not. 110, 15, 40, 60, 70, 130. Okay, so turns out that the average starting salary for UNC geography majors is about $250,000 a year. And of course, when they told my wife that and everyone in her class, they all said, I've got to go to the registrar's office and change my major. And they said, before you leave and go change your major, you might want to think about why that starting salary is so high. So what do you guys think? Why is the UNC salary so high?
Jordan go back and finish his degree.
So Michael Jordan played I mean, he's a basketball player though, right?
Yeah.
But he majored in geography, and he went pro after his junior year. It was 1983, something like that. And so he didn't graduate, right? He just went to the NBA, and then he had 3 good years at the NBA, and all of a sudden he decides, hey, I think I want to finish my degree. And so he finished his degree, and what's his starting salary? He's got Nike, Gatorade, all of these companies paying him lots and lots of money. So here's Michael Jordan. I think it was around $60 million. Right? And here's everybody else down here around like $15,000. And so the average gets pulled up here to $250,000. So kind of interesting, but this illustrates some very important things that we want to keep in mind when it comes to statistics, and that is if you calculate X bar, the sample average. Now this population is small enough that you could actually find the population mean mu. So it's basically the same formula. We'll just write it down. It's the summation of the xi's divided by the sample size. And so every single data point has the same weight. So you get these extreme values, and it pulls the mean far away from your typical sort of data point. So Michael Jordan's salary would be considered an outlier. And you have to ask yourself, what are we going to do with outliers? Should we just throw them out? Well, maybe, but did Michael Jordan use his geography in his career? Sure, it was like a different venue every couple days. You had to learn about all of the weather and all that stuff that goes into traveling around the country all the time. So you might make that argument, but was he making maps and that sort of thing? Probably not. So we could throw him out. That's one thing we could do. Or we could do a different measure of center, and that is to calculate the median. And that's just the point in the middle. So every data point is still included, but the ones that are extreme don't have an excessive influence on this value. So the median is going to be right down here somewhere. But this is important because you can use extreme values to understand skewness. That's something that's big. If you want to pick stocks, what kind of stocks do you want to find? Well, it depends on your utility function, of course, but most people like ones with super big returns, right? They like the Bitcoins or the whatever, Google when they go public, or Facebook. They want something that's got this giant return way out here, uncharacteristic. And you might say, well, that's uncharacteristic, but still, that's what I want. So I want to find out what makes it uncharacteristic, right? So what other variables might you be interested in, or characteristics might you be better off using the median than the mean? So that's the median, this is the mean. What about housing prices? There's some really, really, really expensive houses out there, and Bill Gates' house, from what I understand, is like crazy expensive, and like I don't know if it's true or not, but I heard that he bought a whole neighborhood and tore down all the houses, and then built his house, and it's hundreds of millions of dollars. Well, do you really want that in the calculation for when you guys graduate and decide to buy a house, and you're trying to decide, how much am I going to need for this house? Well, it's not a typical house. So median house price is the measure that's used much more often than the average price house, just for that reason. Average house price, I should say. Okay, so we're going to look at some data that we're going to collect right now from you guys. So I need everybody to answer the next 4 questions, which will actually come in at one time. And then we're going to look at some stuff with Excel, and just kind of do some raw data analysis. So I have 4 questions for you, and I need you to answer them all at the same time with a number, and just separate them with commas. So the first one is, how many hours per week on average do you spend on homework or studying? So you put whatever that is, comma. How many hours per week on average do you spend watching TV, or whatever the equivalent is now, YouTube, Netflix, Hulu, so forth. And number 3, so put a comma, what's your GPA, comma, how old are you? And submit those. And I promise you I will not release any of this information with any identifying characteristics. I will post the spreadsheet on Blackboard, so you can go in and look at it and repeat what we've done in class here. But hopefully we're going to be able to find what the relationship between some of these variables, and understand how some things can help us do, some variables can help us understand other variables. Okay, so we've got 30 so far, and this time I'm not going to cut it off, so please submit something. Okay, is that everybody? I think there's still more out there. We got 55, 56. So let's go ahead and pull this down. Okay, so here's all the data, and I'm just looking through it. Looks like we have all those responses. So let's somehow I can download this. Download. Okay, so what's the first thing we do with data? Okay, before we can even do that, in this case, change the view here so we can see what's going on. This is kind of messy, isn't it? In data analytics, you spend about 90% of your time cleaning the data up. So getting it into a form that you can actually run all the things that you're interested in. Okay, so I don't care how you submit it. I don't care about the screen name, registered participant, and so forth. So I'm going to delete all this stuff. Just going to get rid of it. And so now I've got response, which I'm going to change to homework, comma, TV, comma, GPA, comma, age. All right, so I've got all of these data points. As long as they're separated by commas, I should be able to do the next thing, which is, so this one here is not separated by commas, so I'm going to have to edit that, put a comma there, put a comma there, and put a comma there. And then do we have any others like that? Let's see. Eight question mark. Not sure what that means. But, there's a comma and then no comma, so we'll put a comma behind that. And so don't have an age, it looks like. Okay, so we've got some missing data, we've got some unformatted stuff. Everything looks okay to this point. So what I'm going to do is I'm going to make go to data and go text to columns, and I'm going to say delimit next. Comma is the delimiter that I want to use, and I don't want to use anything else. So we'll say finish, and it didn't do what I wanted it to do because I didn't highlight all the data. So let's try that again. Highlight all the data. Now we're going to delimit with commas, and we'll say finish. Okay, so now we have hours of homework, hours of TV, GPA, and years old. So we got to get rid of some of this stuff because we just want the numbers. So we'll just, you can do it manually, or you could do find and replace. And I think I'll do find and replace. So we'll go like this, and we'll say actually like this. And then we'll go F, replace hours of homework with nothing. All right, never mind. We'll just go on and do it manually. So give me just a sec. Bear with me here. This will be fun, actually. You guys can, if you're not familiar with Excel, then it's something that you want to get familiar with. And you can kind of see what I'm doing here. So 15 to 25, or 20 to 25. Okay, so I don't know exactly what it is, and I need a fixed number. So I have a decision to make. I can either take the average or calculate some value based on this, or I could just say, well, I'm going to throw that data point out. And in this case, I think I'm going to say 22.5. The more information we have, the better. Okay, but let's see, this one, why did that one not work? I don't know. 20. 3.62, 18, maybe there was a double, must have been a, I don't know, that's going to be 10. Okay, so this, we got hours, I want to get rid of. Hours. I assume that's 2.73, not 19. Oh, I see, they put the decimal places in all those. Right. Easier, so we'll just put 8 here. Notice we're missing the age on that one. 6 plus, we'll just put it at 6. 3.4. 10 hours. Okay, so we're missing data on that one. That's fine. 4.5, 4, 24. Is that it? Okay, that's it. So we've got a bunch of data, and the first thing we want to do is, oh, I guess we got to edit these too. 3.92, 2.58, 8, 25, 12, and 25. And we have to do the same thing for this one. All right, this will be quick. 7, 4, 3.1, and 20. Do you have anything else like that? No, it looks good. Okay, so first thing I'm going to do is when I have my data, I've got it. Now it's finally cleaned up, and I can do something with it. And let's just focus on the age variable for a minute and make what's called a dot plot and see if we can make a histogram. And so we've got the raw data. It's unsorted. It's just sitting there looking at it like this. Can I tell anything about it? I mean, sure, I see a few of the values, but it's a big enough data set that even if I scroll down to the bottom, it doesn't really tell me, you know, I don't know if I've seen the maximum, the minimum, anything like that, and I don't really have an idea of how much of these, you know, how many 23-year-olds there are, how many 19-year-olds there are, and so forth. So first thing I could do is make what's called a frequency distribution, and in order to do that, I'm going to select all of the data, and I'm going to come in, I'm going to sort by age, but I want to sort all of the data, so I come here to sort, data, and then sort, and I'll say sort by age, and I want smallest to largest, and so now I've got all of the data sorted. And if I only, you got to be careful, if you only select the age and sort the age, then you lose all the information that connects all of the other variables, or at least connects age to these other ones. So you want to make sure that you do everything here. So age is going to be, looks like we have a couple 18-year-olds, a bunch of 19, 20, 21, 22, 20, and then a couple 24-year-olds. So if I want to count, I'll call it frequency. What I'm going to do is I'm going to use, and there's probably functions built in to do this to Excel, but I'm going to use an if statement. Actually, the first thing I'm going to say is, yeah, I'll use the if statement. So equals if, I'm going to come over here and say if D2 is equal to D1, actually, sorry, hold on. I'm going to start with a 1 here. So I'm going to say there's one 18-year-old. That's the first thing I'm going to do, is count the first one. And then I'm going to put the if statement in. So if 18 is equal to 18, right, if these two are equal, then I'm going to take the frequency and I'm going to add 1 to it. And if they're not equal to each other, then I'm going to start over at 1. Okay, so I should get a 2 here. So I have a 1 18-year-old, 2 18-year-olds. And I'm just going to copy this, and I'm going to paste it all the way down here, the bottom, and I'll say how many 19-year-olds are there. It looks like there's 15 19-year-olds, and then when 19 and, so if you double click on the cell, you see 19 and 20 are not equal to each other, so instead of adding 1 to the previous count, we're going to start over at 1. And so we say 20-year-olds, there's 1, 2, 3, 4, 5, 6, 7. Okay, so 17, 22, 21-year-olds, there's 8, 22-year-olds, there's 7, and 23-year-olds, it looks like there's 6. Okay, so let's just make a dot plot real quick. When we're done with the dot plot, we will take our break and come back and look at the data again after that. Okay, so a dot plot can be formed by highlighting age and frequency, and then come over to insert and say, I believe it's this one here, scatter plot. Okay, so what we have on the x-axis right here is age, and I'm going to rescale these axes. So I want 17 up to let's go to 27, and I'm going to leave the other one as is. So this is what we call a dot plot, and this is a statistic. Graphs are statistics, just like numbers are. And we see that we have 2 18-year-olds, 15 19-year-olds, 17 20-year-olds, and so forth. So we can get a real good idea of the shape of the distribution by looking at something like this. So this is kind of a step above just sorting it. If I sort it, it's easy to see the minimum and the maximum, but it's hard to see the shape. So this tells me that 19 and 20, those are the most common ages. 20, of course, is the mode, because we've got 17 20-year-olds in the class. And but these two being bigger than what we have up here in the right tail suggests that the mean is going to be pulled down a little bit. So we do have some skewness here. And why don't we just calculate the mean really quickly. Move this thing out of the way. So let's say here we've got age, and we want the mean. So the mean is just going to be the average function. Select the data points. The mean age is 20.5, and call that mean. The median, another thing that we can calculate easily, is just median, M-E-D-I-A-N, same data. So the median is 20. And standard deviation, STDEV, is going to be equal to the function STDEV dot. I have two options here. One is .s, one is .p. And I'll talk about the differences between those in a few minutes. But we want S right now because we're talking about the sample standard deviation, because this is a sample. So let's just highlight all that and say, what's the sample standard deviation? Sample standard deviation is 1.52. So the average age is 20.5, the median age is 20, and the standard deviation of the age is 1.5 years. Okay, so let's take a break. We'll start back up in 10 minutes from now. Break. And so this dot plot that we see here, again, is a good way to graphically describe what's going on. And there are better plots than dot plots that are easier to make, except for Excel doesn't make anything easy. So what's an alternative plot that kind of looks like the dot plot? You guys have any ideas? Scatter graph. Okay, this is a scatter graph, and the reason that I put the counts down here is so that we could get the other data point. But that's not what I was thinking. This is, guess what the professor's thinking?
Histogram?
Histogram. Okay, very good. Histogram does basically the same thing as this, but even though Excel does have a histogram function in the data analysis tool pack, it doesn't actually make the histogram. Instead, what it makes is a frequency distribution, and I'm just going to make one of those. Let's just insert some space here. So to make a frequency distribution, all we're doing is counting the number of values that we have for each of, the number of observations we have for each of the values. So age, we know, starts at 18, and then we've got a 19 and 20, 21, 22, 23, and the biggest was 24. And so to get a frequency distribution, we're going to just say, how many 18-year-olds do we have? And you come over here and say there's 2. How many 19-year-olds? Well, we had 15. How many 20-year-olds? We had 17. 21. Now I don't remember the rest of these, so I'm going to have to scroll down. So 21, there was 8. 22, there was 7. 23, there was 6. And then finally 2. So 8, 7, 6, and 2. So this is what we call a frequency distribution, and you can put these numbers into this the Excel histogram function. Now I did hear that Excel does do a histogram now, like just select your data and click, but I haven't been able to figure out how to do it. So if you decide you want to go and mess around with that, you can. And so here I wrote count, but I really should call this frequency. All right, so we're saying we have 2 18-year-olds, 15 19-year-olds, and so forth. Give me a little bit more space here. This helps me kind of see numerically or in a table form the same thing as what I get in this frequency dot plot, or what I would get for a histogram. But what other measure could I use to describe the age, do you think? Instead of looking at the frequency, I could calculate what's called the relative frequency. And the relative frequency says, instead of the actual count, it says what's the proportion of the total data. So how many data points do I have? I'm going to first of all sum all of these things up. So for the age variable, I've got 57. And so if I take 2 divided by 57, that's going to be the relative frequency, or the proportion. Now, I'm actually going to copy this and paste it in for all these other things. But when I do that, H10 is what I want to divide by every time. So if I just copy and paste, why does it say that? It says, hold on, you're dividing by nothing because there's nothing in that cell. So I actually want this to be H10 instead of H11, but I want to be able to copy and paste as well. So any ideas what I can do with Excel? This is a nice little Excel trick. No, I can't, not yet. If I just pull it down, what's going to happen? Let's try that. If I pull this down to here, they're all going to be divided by 0. So somehow what's going on here is this is referencing cell H10, which is relative to H3 by going down 7 spaces or 7 rows. So if I want an absolute cell reference instead of a relative cell reference, dollar signs. Yep, if I put a dollar sign in front of the H, that says lock the column, dollar sign in front of the 10, that says lock the row. And now when I drag this, it's going to always use H10 is the denominator. And if I double click on something, you can see that's the case. So that's a useful trick. If I only want to lock the row, then just put the dollar sign in front of the number. If I only want to lock the column, put it in front of the letter. And there's some trick you can use to cycle through those. I don't remember what it is. But what this is telling me is that 26% of the class is 19. 29% is 20. 14% is 21. 12% is 22, and so forth. So this gives me, again, another quick summary view of what's going on in the class. And all I've done is changed the labels on the y-axis. Okay, the next thing that is going to be very important in this class is the cumulative frequency. What does cumulative frequency mean? Cumulative means you're adding things up, right? So you have, you do that with your parents, don't you? All the times that they're not good to you, you keep track of that. You add it up, and then you go off to college and you say, here's a list. It's worth something. Come visit me or do something nice for me because I kept track of it all. But guess what? They're doing the same thing. So don't try and get too much out of that. Okay, so what does this mean, cumulative? We're going to start at the left side or the low end, and we're going to add as we go along. So you could say, how many 18-year-olds are there? Well, there's 2, so I'm just going to put 2 in there. And then the cumulative value for 19 is going to be 19 or less. So how many 19-year-olds are there? There's 15, and I'm going to add to that whatever I had before, so that gives me 17. Okay, so we're just adding these up as we go. So basically we're saying, what's the proportion that's less than or equal to fill in the number? In this case, 19. Well, we haven't gotten to the proportion part yet, but what's the count that are less than or equal to 19? Okay, and I can just autofill that the rest of the way down. And I'll know I've done it right if the last value, 57, is the total number of observations that I have. All right, so 55, 57, so forth. So that's the cumulative frequency. And what if I want the relative cumulative frequency? That's pretty easy to calculate. All I have to do is the exact same thing as what I did before, so I'm just going to copy that. Notice these, the frequency and the cumulative frequency are the same for the first value that the variable can take on, and same with the relative frequency and the I'm probably spelling something wrong there, but I don't care. So if I just copy and paste all this, that's one way to do it. Just divide the cumulative frequency by 57. or I could just add these things up like I did to get the cumulative frequency. So probability is 1, or the proportion is 1 once I get to the top. That's always going to be the case. We'll talk next week about probability and what kind of values you can expect for probability. But I can't overemphasize how important this concept of cumulative relative frequency is. We're going to use that for the rest of the class. And anytime you're dealing with random variables, you're going to use this notion to add up probabilities associated with random variables that you're interested in. Okay, especially when we get to the continuous random variables, this is going to be just absolutely key. One of the most important things that you're ever going to learn in this class is this idea of a relative frequency. So being able to add up the probabilities, so I could say, what's the probability of having someone in the class less than or equal to 21 years of age? Well, there's a couple ways I could get that. I could come over here and say, here's 18, 19, 20. So I add all those numbers up. Oh, that's given to me right here, 73%. So I don't have to worry about messing with all this other stuff. All I'm doing is saying, okay, here's the relative cumulative frequency. If I want the probability that somebody's older than 21, I can get that from the relative cumulative frequency table by just taking 1 minus that value. So if they're 22 or 23 or 24, that's going to be 1 minus that value, so 26.31%. Okay, so more about that next time, but just keep in mind that's something that you really want to understand well. Okay, so what else can we do with all of this data that we have? I'm going to get rid of this frequency. Do I want to get rid of that? No, I'll leave it in. What else can we do here? I'll leave it in, but I'm just going to kind of move everything over. Well, if we have multiple variables, we can look at how the variables are related to each other. And what tool do you think is the go-to for that? There's actually a couple of them. There's one that's numeric and there's one that's graphical. So what are we going to look? Let's look at the graph first. I want to see what the relationship is between GPA and homework. I mean, what do you think the relationship's going to be like from the get-go? The more homework you do, the higher your GPA. Is that a good, basic assumption? Well, that might not be true. I don't know. Let's see. So I'm going to come over here. I'm going to say here's homework, and here's GPA, and I've got both of those selected. I'm going to go insert, and I'm going to go scatter. There's the scatter plot. Now, it doesn't look like there's much of a relationship here, but let's change the let's see. So GPA, let's say GPA goes from 2.5 looks like low, so go from 2.25, and the highest we have is 4, so we'll go up to 4.25. Okay, and then age, sorry, not age, hours. Okay, so that looks okay. It goes from 0 to 45. Nobody spends 45, but we'll just leave that as is. And why did that not take? What's going on with this thing? Well, okay. Excel has thwarted me once again, but that's all right. So what we have here is on the y-axis, we've got GPA. On the x-axis, we have study time. And does it look like there's a relationship between these things? So what does that mean? Is there a relationship between these things? If there's a relationship, that means if I know one of the variables, that helps me understand the other variable. And typically in a situation like this, you would be looking for a straight line trend. And there kind of is a straight line trend here, but the straight line looks like it's basically flat, horizontal. Okay, so I would start off by looking at a chart like this and then say, okay, well, let's actually do a calculation instead of looking at a picture. Let's actually look at a number and a numerical measure, and we'll find out later in class that once we do that, we can actually perform a test. Move this chart out of the way. Okay, so I want to get what's called a correlation matrix. So I'm going to go over here and call this, so this is the correlation. And so what am I going to have? Homework, and then TV, and then GPA, and age. I'm going to paste that special transpose. Okay, so the correlation of homework with itself is 100%, TV with itself is 100%, and age with itself is 100%. Now I want to know what's the correlation between, what do we have, homework and GPA. So the function correl says let's select homework, comma, and then array 2 is going to be GPA. I'm going to come up here to GPA, select that one, and say OK. And it's giving me an error. Why is it giving me an error? Because we've got some missing data. So this is looking for this last observation that has 10 for the homework. Let's just get rid of that one, and or actually let's not get rid of it. Let's just edit the data that we're putting in here. So instead of going to 60, let's go to 59, and that should give us a number. So homework and GPA correlation is almost 0. You see it here, negative 0.005. Statistically, there's going to be no difference between that and 0, and what I mean by that you'll find out later in class. But okay, what else do we want to know? What's the relationship between homework and TV? What do you think about that one? Think there's going to be a relationship? The more homework you do, the less time you have to watch TV, right? Is that a good theory? Unless what? Unless you think you know how to multitask. You watch TV while you do your homework. Anybody in that boat? Okay. Now whether you can really focus on the TV and the homework, that I guess that's another question. But still, you're doing homework and you're watching TV, so there is an interaction or an intersection between these things. But we would find this same way. Correlation, and here we have TV, comma, and then let's come up here to homework. And again, I don't want to get this last point because there's nothing to correlate that one, so the value's not going to work. And here we have a 20% correlation. So 0.2 that actually kind of surprises me. Let's look at the scatter plot for this. So here's, I don't know which one's which. Somebody watches 40 hours of TV and they do 40 hours of homework. And I guess probably they're doing a little bit of both at the same time is my guess. But you can kind of see there is a straight line relationship. The best straight line that fits this data is not a flat line, it turns out. And maybe this point here is influential. So just for fun, let's find it and get rid of it. 40. Okay, so we're just going to delete this for a second and see how that changes. First of all, the graph. So is that an influential point? Yeah, probably. It's hard to tell from the graph, but if you look at the correlation matrix, you see that that is a very influential point. I mean, we haven't measured that statistically, but it drops from 0.2 to 0.04. So let's just put that back in. And now let's find the correlation between, what else do we need? Age and homework, TV and age, GPA and TV, and then GPA and age. So do I want to really do all that stuff all at once? Maybe not, but there's a quicker way to do this. But we're going to do GPA and TV. So here's GPA. And here's TV. And we'll say OK. So we get GPA and TV. Again, no relationship there. That's basically 0. So now it's a question of age versus homework, TV, and GPA. And I'm not going to plug all those in. Instead, I'm going to refer you over here to data analysis. If you use the correlation matrix, the correlation function, you can select all of these things. Like this. Scroll all the way down. And here I'm going to stop short of those last two. And then I'm going to say OK. And there are labels in the first row. And I'll say OK. And here's the correlation matrix that I get the easy way, which is slightly different than the one that we had. I don't know why it's different. I guess because we dropped out a couple of data points, but I think the function it's calling is the same thing. So could come back over here and try and mess around with it and match those up. So the TV, if we go down to 58 instead of 59. Okay, so go down to 58 instead of 59. So we leave that last data point off. That does change it to match what the other function is giving us. Okay, so so we've got correlation matrices. We've got we cleaned up the data. One other thing that we're going to want to know about, and then we'll be done with class for today, is standardizing variables. And I'll just show you very quickly how to do this. By the way, I'm about this close to getting Excel to work on the exam with the Blockdown browser. So I'm not going to jump for joy yet, but I will tell you, don't ignore the Excel stuff. Hopefully you'll be able to use it on the exams. I think you will, but this is important stuff to know how to do. So what does it mean to have a standardized variable? If I take my random variable x and subtract from it the mean, which is mu, and divide by the standard deviation. Has anybody seen this before? This is so common it has its own name. It's called z. And that's what we call a z-score. So if you take x minus mu, if x is in dollars and mu is in dollars, then the numerator here is in dollars. And it turns out that sigma is also going to be in dollars. So what are the units on z? You have dollars in the numerator and dollars in the denominator. There are no units. The units cancel out. So you can use this standard z value or standardized measure to compare things like apples and oranges. Everybody always told you couldn't do that, right? Well, it turns out you can do that if you get rid of the units. And so what we're really doing is saying how many standard deviations. So you could say the units are standard deviations. How many standard deviations above or below the mean is your value of x? And that's going to be this z value. And the empirical rule tells us something that's very important. It says in the x world, if we have mu right in the middle, so if we have a bell-shaped symmetric distribution, then we have the empirical rule, and that says plus or minus 1, plus or minus 2, plus or minus 3 standard deviations. So we have mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. These things correspond to z values. In other words, if I took mu and I subtracted it from x and divided by sigma, what do I get? I get 0. And if I take mu plus sigma, subtract mu, divide that by sigma, I get sigma divided by sigma, which is just 1, 2, and 3. So all of these points correspond with each other. And it turns out that the empirical rule says that about 68% of the data is between -1 and 1. And about 95% is within plus or minus 2 standard deviations, and 99.7% or thereabouts, or in other words, almost all of the data is within plus or minus 3 standard deviations. So this is really useful. If I want to know how likely an observation is, I can calculate still this here. I can calculate the z-scores by hold on a second, maybe it's even bigger. Alright, Excel. Oh, it's the easiest thing to get done what you want to do. Right, so let me just throw this in here. Okay, so I want the mean for the age. I want the mean and standard deviation for the age, which is going to be this stuff. The average, that's what I want. Okay, this is giving me, let's try this one more time. Average of all this stuff and then I want the standard deviation. So it's going to be D2 to D58. Okay, so there we go, 1.52 and 20.5. Okay, so that's for the age. GPA, I'm going to do the same thing. I'm just going to copy and paste. Just get rid of the median for a minute. And GPA, and then we got TV, and we have homework. So I'm just going to copy and paste all this here, and I have the mean and the standard deviation for both of these things, or rather for all of these things. So if I want to find the z-score, what do I need to do? Let's say this is the homework.z, so this is going to be the z-score for the homework. I just have to use that formula, x minus mu divided by sigma. Now I don't know what mu is, so I'm going to use this x bar to estimate it. So I'm going to get x, so that's 5, minus the mean divided by standard deviation. So this first one, homework of 5, that's a little over 5 units below the mean, but it turns out to be negative 0.83 standard deviations below the mean. So if I want to do this for all of those values, I need to first lock the mean and the standard deviation, and now I can just double click on that. And it says if the mean, or sorry, if the value of 22.5 for homework, how many standard deviations above the mean is that? It's 1.36 standard deviations. So this z thing is very useful, and I can just come down here and sort through it and say, you know, what kind of values do I have? Here's 2.9. That's pretty big. That's close to 3. How many should I expect to be bigger than 3? Well, not very many. And here's 1 at 3.55. So that's very large, at least according to the empirical rule. And you know, maybe I don't have the right type of data to use the empirical rule. But let's do the same thing, just quick for television. Okay, so this is going to be equal to, I'll just paste it in here and then come in and edit this to get the right thing. So I don't want K in this case, I want L. I'm going to change that to L. Change that to L. And I can see now I've got TV B2 minus the mean for TV divided by the standard deviation for TV. And so I'm going to do that again. Okay, so I've got these z values. So I'm going to label this correct, TV.z. And we see 2.7. That's the biggest one so far. And nothing really extraordinary in this case. So this is something that's also very useful. So are there questions you guys have about any of this stuff? All right, well, I will post this Excel spreadsheet on Blackboard. And let me just point out one thing on Blackboard that I really need you to do before we meet next time. And that is under the week 3 folder, there's an experiment that I need you to go and check out, and it's an ESP experiment. So just click on this link and it will bring you here and kind of give you instructions on what to do, and So try this out. Come next week prepared to discuss it, and we'll see you guys next week.